Today we're going to talk about a method of solving equilibrium problems called the Rice method. Rice stands for reaction, initial concentration of the substances, change in concentration of the substances involved in the reaction, and the equilibrium concentration. And all of these values have to be in moles per liter. It's very important to remember that concentration, that all of our numerical values that we're working with in equilibrium problems must be in molarity for this method to work. So let's look at this first example. I could read through the explanation, but until we actually do a problem, it's not going to make as much sense. So let's talk about, in this first section, problems in which we can do something called neglect X. Now, what does that mean? Well, we've got this reaction here where we've got NOCl reacting to form NO, nitrogen monoxide, and chlorine gas. And it says that at 35 degrees Celsius, the equilibrium constant is 1.6 times 10 to the negative fifth. And it says that we're going to start out with 1 mole of NOCl in a 2-liter flask. Now, make sure you pay attention to what size flask it's in, because that's going to make a difference if it doesn't give us molarity in the beginning, but gives us moles. We're going to have to make sure and calculate that. So it wants to know what the equilibrium concentrations will be, and then how many grams of NOCl will be in the flask at equilibrium. So using the Rice method, the first is to write down the reaction. So the 2NOCl, we're going to write down the fact that it's reacting to form NO and Cl2. Now, that's the reaction. We're going to put the initial concentration, we're going to put the change in concentration, and we're going to put the equilibrium concentrations, and we're going to put a line here. And that's going to be kind of the skeleton for all our problems. Very important to remember to notice whether it's telling us an initial concentration, whether it's telling us a change, or whether it's telling us a final equilibrium concentration. Now, it does give us an equilibrium constant, and it's talking about it in terms of concentration, so this we know to start out. Now, this doesn't belong in the Rice portion of the problem, but it is going to be important to us here in just a couple of minutes. It says we're beginning with 1 mole of NOCl in a 2-liter flask. Well, the very first thing we've got to do is get that converted to molarity, moles per liter. So if we've got 1 mole and it's in a 2-liter flask, then we've got a 0.5 molar solution, technically 0.50. So that's going to be our initial concentration of our NOCl, so 0.50 molar. And at the beginning, we just put in some NOCl. At the beginning, there are no products, so both of these are going to be 0. Both the NO and the Cl2 are going to be 0 to begin with. As the reaction proceeds, we're going to lose some NOCl. For every 2 NOCls that we lose, we're going to produce 2 NOs and 1 Cl. So we're going to get some Cl. We're going to call Cl X. So we're going to add in some Cl in some concentration of Cl, some moles per liter. And we're going to add in some NO, but think about it. That's going to be 2 times as much that we're going to produce as we get chlorine. And we're going to lose 2x of our reactant. It's going to react, so minus 2x for our reactant. So we're using these coefficients to come up with these values for x. This is an understood 1 in front for both of these. So our equilibrium concentration is going to be 0.5, our concentration, minus x, and I'm not going to put in units now because the units are just end up being confusing because there are no units for our final equilibrium constants anyway. So 0.50 minus 2x for our NOCl. We've got just 0 plus 2x, or just 2x for our NO, and x for our Cl2. So those are equilibrium concentrations. Very important to note. You might want to jot this down. The equilibrium concentrations are what we use to get our equilibrium constant. When you make your equilibrium expression, those are the values that are going to go in. So these are incredibly important. These equilibrium concentrations are very important. That's what's going to go in our equilibrium expression. And what is our equilibrium expression here? That Kc is equal to the concentration of NO squared times the concentration of Cl2, we've done this before, over the concentration of NaCl squared. And up above, remember, we wrote down that, and it gave us that Kc was 1.6 times 10 to the negative third. So when we plug in values, NO, the equilibrium constant, was 2x, and that's going to be squared. And chlorine is x, and NaCl is 0.50 minus 2x, and that's going to be squared. Now here's where the neglect x part comes in. X is, when we've got a very small, quite small equilibrium constant, we end up with an x value that is very small. Let's say our x value ends up being 0.0001. If you subtract 0.0001 from 0.5, or even 0.0002 from 0.5 to 2 sig figs, is that going to make any difference to the value? And the answer is no, it will not. So the rule is that we can neglect any x, subtracted or added x only. We can neglect any x that is added or subtracted as long as it is less than 5% of our original value. Now, AP's rule is that it's always going to be less than 5% of the original value, because they're not going to make us use the quadratic equation on the test, which is what you'd have to use if we couldn't neglect x in this case. So since we don't have to do that, fortunately, we're always going to be able to neglect x on our problems. If we have time, we'll do some problems where we have to use the quadratic equation, but that'll be after we're ready for the AP test, because we don't need to have it for the AP test. So what does that mean? It means any added or subtracted x can be neglected. I can't get rid of the x's on top. They're not added or subtracted, they're multiplied. Now, AP is also very strict about the fact that you have to show why you did that, or show that you know you're neglecting x. So the rule is that you have to show this. You have to show it in terms of, or show the expression again with the x dropped out. So I'm going to go ahead and solve for this top part. We've got 2x squared, which is 4x squared. So if you would agree, this is 4x squared here when you work out this term, times x means we've got 4x cubed on top. So this is what we've got to solve with. I'm going to extend this a little bit so that we can continue writing. When I solve this, I end up with 4x cubed being equal to, and I'm going to multiply 1.6 times 10 to the negative third and multiply it by this 0.50 squared here. And when I do, I get 4 times 10 to the negative sixth. And I get that x cubed, or x cubed is 1 times 10 to the negative sixth. X is 1 times 10 to the negative second. Now, what does that mean? I've got an x. What is that telling me? Well, now it's time to go back up here. We know X now, and we know what all of these terms are, all of these values are in terms of X, and it wants to know the concentrations for all of them. So let's do that real quick. I know that X is equal to the concentration of our Cl2. So that's going to be 0.010. I just wrote it in standard notation, molar Cl2. I know that our NO, if you remember up here, was 2x. Let's look back up there and remind ourselves, 2x right here. So 2x for our NO value. And that's going to be 0.02 molar. And then our 0.50 minus 2x is our value for the concentration of NaCl. If you'll look back up at the table, you can see that. And when you subtract that out, you get 0.48 molar NaCl. So those are our concentrations of each of our substances. So it asked for this, so you would want to box them. But don't forget the last question. The last question said, what is the number of grams of NaCl remaining in the container at equilibrium? So if you've got 0.48 moles per liter of our NaCl, and remember it was a 2-liter flask, so I'm going to multiply that by 2 liters because it was in a 2-liter flask. And then in order to get it to grams, I'm going to multiply by its molar mass. And if you add up nitrogen, oxygen, chlorine, you get 65.46 grams per mole. That gives us a value of 62.8 grams of NaCl. And since it gave us values in 2 sig figs, I would say that we would need to say that there are 63 grams of NaCl for our final answer to 2 sig figs. So that's our first example. And I want to do one more example just to make sure we've got it. Let's look at the next page here. In this case, it says calculate the number of moles of chlorine gas produced at equilibrium in a 10-liter flask, smiley face, when 2 moles of phosphorus pentachloride is heated or are heated to 150 degrees Celsius. And it gives us a Kc value right here. So we know we've already got the reaction here. We need initial, we need change, we need equilibrium. So let's get those values first. We know our reaction. Our initial concentration we're going to have to calculate because it gave it to us in moles. If we've got 2.0 moles and we had it in a 10.0 liter flask, that gives us 0.20 molar PCl5 to start this reaction. So that's our beginning concentration, 0.20 molar. We don't have any of the other 2 substances. And our change is going to be minus X for PCl5. All of these are 1 to 1 to 1 to 1. So minus X for PCl5. Remember, as a product, that's going to be plus X and plus X for both PCl3 and chlorine. So our equilibrium concentrations are going to be 0.20 minus X, X for PCl3 and X for Cl2. So now the next thing we need to do is to write our expression. And we're dealing with these values in terms of concentration. So Kc is equal to concentration of PCl3 times the concentration of Cl2 over the concentration of PCl5. So there's our expression. It gave us a value for Kc of 4.10 times 10 to the minus 6. both PCl3 and Cl2 are X, so we can put X. We could also put X squared. Either way, it doesn't matter. And PCl5 is 0.20 minus X. Remember, we're going to be able to neglect any added or subtracted X. So this is going to be approximately equal to X squared over 0.20. This gives us a value of X squared being equal to 8.20 times 10 to the minus 7th. And X then, square root of that, is going to be 9.06 times 10 to the minus 4th. Well, what does that tell us? Well, it tells us that X, and since it asks us about chlorine, chlorine is X, that's convenient. So that tells us the molarity of chlorine. So let's write that down real quick. X equals the concentration of chlorine equals 9.06 times 10 to the minus 4th molar. Now here's the problem. That's not what it asked for. What did it ask for? It asked for moles of chlorine. So remember that molarity is moles over liters. So all I need to do to get this into moles is to simply multiply by the 10-liter flask that we started with. And that's going to give us a value of 9.06, or probably to correct sig figs, we need to go to 2 sig figs. 9.1 times 10 to the negative third moles of chlorine. So be careful what it gives you. Be careful what it asks you to find. Make sure you're actually finding what it asks you for.